Okay, good evening. This is Professor David J. Delosreyes. My topic for tonight will be a continuation of my subject matter AC machines, and I am now on lesson number 61. And the title of the topic will be example problem on the concentration of the problem for tonight will be in the computation of the so-called pitch and distribution factor. Pitch and distribution factor are actually the factors that will correct the induced voltage per phase of any alternator because there is no such thing as a perfect alternator from the theoretical value. So by multiplying the theoretical induced voltage by this pitch factor and distribution factor, we will be getting the exact generated voltage for any alternator. Okay, let's proceed. The subject matter for tonight will be AC machines, lesson number 61, and the title of the topic will be example problem on the computation of pitch and the so-called distribution factor. Okay, there is an erratum on lesson number 60. I will just make a take note of this one because somebody might notice it on the so-called coil span on lesson number 60. There was a little bit error on the computation of the coil span. It should be corrected, and the correction should be on this topic for tonight. The proper solution on the coil span will be the solution for tonight. So whatever you notice on lesson number 60, just proceed to lesson number 61 because there was a little bit discrepancy on the number of slots. So I am making this notice that there was a little bit error on the coil span for lesson number 60, and the proper correction should be seen for this lesson number 61. Okay, let's proceed. I will try to read the problem. A 90 slot stator has three phases, plural, 6 poles, each coil which spans from slot 1 to 14. The problem is asking calculate the pitch factor and the so-called distribution factor. And the design of alternators, the pitch factor and distribution factor is actually very important because we must have to multiply the theoretical induced voltage by these factors here for us to determine the exact voltage generated by the alternators going to our step-up power transformers going to our transmission lines. So for tonight, we will be calculating the, we are asked to compute for the pitch factor with the given data and the so-called distribution factor. With regards to lesson number 60, there was a little bit discrepancy on the coil span. So if you would notice that one while you are watching lesson number 60, just proceed with this, and the proper way on how to compute for the coil span will be on this one. I missed one slot, okay? Okay, let's try to bring out the given. The total number of slots for the given alternator, supposed to be this is an alternator. The total number of slots is 90. So it's a very big one. Okay? The number of phases, for power generation, it's always a 3-phase. 3. So it could either be Y connected or delta connected, it's 3-phase. The number of poles is 6. It's not so many, so maybe this alternator will run at a little bit near 1000 RPM maybe. Because if it's a 12 pole, more or less the RPM is on the range 600 RPM. Because we are avoiding vibrations, okay, for us to construct a machine foundation not too expensive. Because we got a big machine foundation, okay, concrete is expensive, and the vibrations are actually very big. So we try to minimize the speed of the alternator as it rotates, okay, to generate voltage. The given condition of the problem, this is very critical. This is where I made one mistake on this slot. Coil span slots is actually 1 to 14. This coil span is very critical because coil span is actually if conductor number 1 enters slot number 1, this is slot number 1. This is 1 to 15. Enters at slot number 1, okay? It will go at the back, then it will enter slot number 14. Okay, that's the meaning of this. It goes out at slot number 1, then it will come back at slot number 14. Okay, it goes in here, it goes to the back, then it will come back, then it will enter slot number 14. So that's the meaning of the coil span slots is actually 1 to 14. But this is very critical in the so-called computation of the so-called pitch factor. Because if you made a mistake of one slot, the error is not so much because 1 degree error is not very noticeable. But if we are talking concepts, it is wrong, right? So we must have to correct it. Okay, let's proceed. So this should be the given figure of the stator of the alternator spread out. This is slots where the conductors are placed embedded, and these are the teeth, tooth. Okay, so this should be slot number 1. I marked this one as slot number 1. This is slot number 5. This is slot number 10, and this is slot number 14. Meaning to say, it enters slot number 1 for the coil, it goes back, it goes in front again, it will enter here. Okay, that's the meaning of the coil span 1 to 14. But it's very critical. I will tell you where I made the error. Okay. Let's try to define first what is coil span. Coil span is the number of coil slots spanned by the sides of the coil. Because in each slot, there are 2 sides of the coil. This is the first coil, this is the second coil. Because if the winding is what they call this lap winding, it goes in here, it goes to the back, it comes back here, right? So if the winding is a lap winding, okay, it will move what they call this 1 slot forward to maintain the 14 slot given coil span. So it come out here, then it will enter here. Something like, I will erase this one. It will enter here to maintain the coil span 1 to 14. So it is going like this, right? But it's moving on this side. Okay, it starts at 1, it goes out at 14, then it will, what they call this, if this is the other side of the extension of 14, if this is number 1, this should be slot 90. Slot 90, because there are 90 slots, right? So as it come out from 14, it goes to 90 to maintain the 14 slots coil span. Okay, then it will go back here, then it will go to maybe, what slot will be this one? Maybe 89. It will go to 89. So for a lap winding. But for a wave winding, that's another story, right? That's another. I am just telling you how the winding is actually wound around the slots. Okay? But the main thing here is the coil span should be a number from 1 to 14. So if it comes out here, it will back out one slot to the left, it will go to 90. Okay? Then it will go back again, it will come out at slot number 13 maybe. Then it will enter here at 89 to maintain the so-called lap winding connection. If the connection is lap winding. Okay, I will try to erase this one. Okay? So that's coil span. Coil span is by definition is the number of slots. So this is very critical. Okay, let's count the number of slots for us to correct the error from lesson number 60. The number of slots that's full is actually because if the coil span is 1 and 14, the coil span is actually this one. Right? Okay, let's try to count the number of slots. Disregard first is 1. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we got full 12 slots. This is full. Right? The one in between 1 and 14, there are 12 slots which is full. Complete, right? But considering slot number 1, the measurement is actually at the center. So we are only considering 1/2 slot over here. And on the other side, on slot number 14, we are only considering 1/2 slot. So the not full slot is actually 2 times 1/2, which is actually equal to 1 slot. Okay? This is 1/2. This is 1/2, but it is 2, right? So there is 1 slot. So the total number of slots between, if the coil span is from 1 to 14, it should be 12 plus 1. And this should be equal to 13 slots. Okay? So we got 13 slots. And supposed to be the general formula on how to compute for this 13 here should be, we are given slot 1 to 14, right? So it should be 14 minus 1. Okay? Which is equal to 13. So this is 13. I made the mistake on lesson number 60. I made this just simply 14. It should be 14 minus 1. Okay? But the proper way on how to compute for the coil span will be the given slots minus 1. So it should be 14 minus 1. So it should be 13. So this is 13. But the physical, what you call this physical proof that it is 13 is actually we counted 12 in between. And we counted 2, which is only 1/2. 2 times 1/2 is 1. So 1 plus 12 will be 13. 13. And the proper way should be, if we are given the coil span from 1 to 14, it should be the total coil slots in between 1 to 14 will be 14 minus 1, which is 13. That's where I made a mistake on lesson number 60. Sorry for that one. I'm just correcting the concept. Right? Okay, let's try to compute for P degree. We need P degree. Because in the computation of the pitch factor, we should know P degree. Okay? This is where the critical part of the solution from lesson number 60. P degree will be coil span divided by slots per pole times 180 degrees. The coil span is actually the one we computed. Coil span is actually, let's try to compute first for slots per pole. It should be 90 over 6 and slots per pole is 15. So we now know this one to be 15. Okay, this is 180, this is given. The problem here is the coil span. What will be the value of the coil span? The coil span is the one we illustrated here. It should be 13 slots. Should be, this is the general formula. If the coil span is 1 to 14, it should be 14 minus 1, which is 13. Right? This is 13. And the physical proof is this one. There are 12 full slots in between, and there are 2 half slots in between. 1/2 here, 1/2 here, and there are 12, so it's 13. So this is 13. This is 13. So we have corrected the error from lesson number 60. Sorry for that one, guys. So this should now be 13 over 15. Slots per pole is 15, right? 13 over 15 times 180. So P degree is only 156 degrees. Since P degree is not equal to 180 degrees, right? It should be a fractional pitch winding, fractional. It's not full pitch, fractional. Because if P degree is exactly 180 degrees, meaning to say if it enters 1, then it goes to 15, that's full pitch. But the given problem is just from 1 to 14. So this is, it enters 1, it goes out of 14, and that's fractional pitch. So P degree is not equal to 180 degrees, it's only 156. So the equivalent of this 13 slots is only 156 degrees. Right? Okay, let's now try to compute for the P degree. Pitch factor. Pitch factor is sine of P degree over 2. P degree is how we computed this one. The explanation is this one. Okay, it should be sine of 156 degrees over 2. It will be sine of 78 degrees. And this should be 0.978. Okay. For the so-called distribution factor, this should be the formula. It's not so critical because we just have to compute for small letter n and for d degree. The d degree is actually the total degrees in between slots. Okay, how many degrees is the distance between slots? And actually we could compute for that one. For the small letter n, it will be slots per pole divided by the number of phases. That's a general formula. We can't do anything about it, right? We cannot make the mistake, not unless you made a mistake in the computation of slots per pole, you made a mistake. But if you are accurate in the computation of small letter n, we could compute for the slots per pole to be correct. So slots per pole will be slots per pole divided by the number of phases. Slots per pole is actually 15. So this is 15. The number of phases is 3 phase. This is 3. So this is small letter in here is actually 5. And d degree between a south pole and a north pole, if this is north, the distance between a north pole and a south pole in a stator is actually 180 degrees. So if we try to compute the total distance between each slot, okay, we just take 180 degrees, that's a full pitch, right? And we know the total number of slots per pole to be 15. So d degree will be 12 degrees. So meaning to say, in between slots, this is 12 degrees. We can't make a mistake on that one. It's just a simple computation, right? Unlike on the pitch factor, if you made a mistake on the P degree, your pitch factor will be wrong. But it's not so much because your error is only 1 degree or 2 degrees. It's not noticeable. But if we try to follow the concept, it's wrong, right? So the distribution factor now will be given by this formula. We now know n, we now know d degree, right? So this should be sine of n is small letter n is 5. D degree, the distance between slots is 12 degrees over 2, close quantity. This is n again, sine of d degree over 2. 5 times 12 is 60 divided by 2, so this should now, the numerator is sine of 30 degrees. The denominator will be 5 sine of 12 over 2 will be 6 degrees. Okay? And if we try to compute for the value of this, the value of the distribution factor is 0.956. There is not so much danger in making an error in the computation of the distribution factor. Because in the computation, we will just compute for n, and we will just compute for the d degree. We can't make a mistake in here. Unlike in the pitch factor, if your analysis on the computation of the slots from 1 to 14 is wrong, you're wrong already. That's why I corrected the error from lesson number 60. I missed one slot, and the proper way on how to eradicate that problem is by showing that the total number of slots in here, the total full slots is 12. The half slot is 1. This is 1, 2. So this is 2 times 1 half. 2 times 1 half is 1. So the total number of slots between slots 1 and 14 should be 13. Okay. The last time around, I make it as simply 14. Okay, that's it, guys. So the next time around, we'll be having another concept on the so-called study of alternator. It's a different topic. We are now through with the so-called distribution factor and pitch factor. I'm just repeating our error on the pitch factor. Okay? Nobody's perfect. At least I have corrected it. Okay, this is Professor David J. DelosReyes from Los Angeles. It's good morning already.